10.4 billion light years away, at a point in cosmic history when the universe was barely a quarter of its current age, there's a structure that, according to the standard model of how the universe assembled itself, should not have finished forming yet. Not almost finished, not partially formed. According to the physics astronomers have relied on for decades to describe how galaxies gather together into larger structures. What should exist at this exact point in cosmic time is a loose, disorganized scattering of young, actively star-forming galaxies, still in the early stages of being pulled together by gravity, still chaotic, still assembling. Instead, when the James Webb Space Telescope turned its mirror toward this exact patch of sky, it found something that looks almost exactly like the kind of massive, tightly bound, fully organized galaxy cluster you would expect to see much closer to home in the modern, nearby universe, billions of years more evolved than it has any right to be. And that alone would have been a significant discovery on its own. But then, Webb's data revealed something else, something so unexpected that the research team says it set an entirely new distance record and forced them to rethink how quickly matter in the early universe could actually organize itself into the densest structures we know how to detect. Right now, in the summer of 2026, this discovery is actively rewriting a piece of cosmology. And it started more than a decade ago as nothing more than a faint, barely detectable smudge in an X-ray survey that almost nobody paid attention to at the time. Stick around, because by the end of this video, you'll understand exactly what this structure is, why its existence this early is such a serious problem for existing models, and what scientists think it might mean for one of the biggest unsolved mysteries in physics, the true distribution of dark matter across the universe. And if you want to see where this research goes next, because the team behind it has explicitly said the hunt is now on for more objects like this one, subscribe now, because this story is only getting started. To understand why this discovery landed the way it did, you have to go back to 2014, to a fairly routine astronomical survey that was never specifically designed to find anything like what it eventually turned up. The European Space Agency's XMM Newton spacecraft, an X-ray observatory that has been in operation since 1999, was running what astronomers called the XXL survey, a wide systematic scan of roughly 25 square degrees of sky specifically designed to catalog distant galaxy clusters by detecting the faint X-ray glow given off by the superheated gas that fills the space between galaxies inside a cluster buried. Within that survey data, researchers flagged a faint, extended source of X-ray emission, distinct enough from a normal point source to suggest it might be coming from an actual cluster rather than a single object, but faint enough that pinning down exactly what it was and how far away it actually sat would take years of follow-up observation across multiple telescopes and instruments. That faint source was formally cataloged and named XLSSC-122 in a 2013 paper led by astronomer John Willis, and for the next several years, it existed mostly as a promising but unconfirmed candidate, one faint smudge among many in a catalog of distant cluster candidates still waiting on definitive follow-up data to nail down its true distance and true nature. The first real hints that XLSSC-122 might be something genuinely unusual came from a series of follow-up observations conducted throughout the mid-2010s, using instruments capable of detecting a very specific phenomenon called the Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background radiation caused by hot electrons in a galaxy cluster's gas, scattering photons of that ancient background light. Detecting this effect confirmed that XLSSC-122 did, in fact, contain hot, ionized gas consistent with a genuine galaxy cluster's intra-cluster medium, not simply a chance alignment of unrelated background sources. Deeper X-ray follow-up observations pushed the case further, eventually allowing researchers to measure the temperature of that intra-cluster gas directly, and the number that came back was striking on its own, roughly 60 million degrees Kelvin, hot enough that the gas was already behaving exactly like the mature, well-developed intra-cluster medium found in galaxy clusters much closer to Earth, and much later in cosmic history, a temperature that took multiple dedicated observing campaigns across several different X-ray instruments to pin down with any real confidence. Even more strikingly, that gas was already enriched with heavier elements, metals forged inside stars and blasted outward by supernovae, at a level roughly comparable to clusters found in the much more recent, much more evolved universe. This was, from the very earliest indications, a distant object that kept behaving like it wasn't distant at all, at least not in the sense of appearing young, disorganized, and freshly assembled the way theory said it should. The full picture snapped into focus in 2020, when a team led by John Willis published spectroscopic observations of XLSSC-122 using the Hubble Space Telescope's Wide Field Camera 3, definitively confirming 37 individual member galaxies belonging to the cluster and pinning down its precise redshift at 1.98, corresponding to a look-back time of 10.4 billion years, meaning astronomers were looking at light that left this cluster when the universe itself was only about 3.4 billion years old, an era astronomers often refer to as cosmic noon, the period when galaxy clusters across the universe were generally understood to have only just begun assembling into recognizable structures, a benchmark that took years of dedicated telescope time across multiple observing runs to properly nail down. But the detail in that 2020 paper that genuinely stunned the field involved the age of the individual stars inside those 37 member galaxies. Using careful photometric analysis, Willis and his team determined the galaxies carried a mean, dust-free stellar age of roughly 3 billion years, which meant, working backward through cosmic time, that star formation inside this cluster's galaxies had actually begun when the universe itself was only around 370 million years old, one of the very earliest windows of cosmic history astronomers have any direct evidence for at all. In other words, XLSSC 122 was not simply an early cluster. It was a cluster whose individual member galaxies had already been quietly forming stars for billions of years by the time astronomers were observing them, meaning the entire assembly process, star formation, galaxy formation, and the gravitational gathering of those galaxies into an organized cluster had all been running dramatically faster and dramatically earlier than the standard model of cosmic structure formation comfortably predicted. Researchers studying the cluster's member galaxies in follow-up work found that the vast majority of them, roughly 88%, were already quenched, meaning they had largely stopped actively forming new stars, another hallmark typically associated with much older, much more evolved galaxy populations, not galaxies caught during the supposedly chaotic early assembly phase of cosmic noon. That combination of findings alone would have made XLSSC 122 one of the more scientifically important distant cluster discoveries of the decade. But Hubble, for all its extraordinary contributions to the case, had reached the practical limit of what it could reveal about this particular object. And that is where the James Webb Space Telescope entered the story, in observations carried out and analyzed through 2025 and into 2026 by a team led by Kyle Finner, a staff scientist at Caltech's Infrared Processing and Analysis Center. Finner's team pointed Webb's NIRCam instrument directly at XLSSC 122, expecting to build on Hubble's earlier work with sharper imaging and deeper infrared sensitivity. What they found instead, buried in that new data, immediately grabbed the entire team's attention. Scattered around the cluster's core, Webb's images revealed a set of long, curved, distorted arcs of light, unmistakable signatures of an extremely rare and specific phenomenon called strong gravitational lensing, in which the sheer mass of a foreground object, in this case the galaxy cluster itself, physically bends and distorts space-time enough to warp, stretch, and magnify the light of much more distant galaxies sitting directly behind it from Earth's point of view. Finner later described the moment plainly, recalling the excitement of the team immediately recognizing they were looking at strong lensing coming directly from this specific cluster, a phenomenon Hubble's earlier observations of the exact same object had never been sharp enough or sensitive enough to reveal at all. That single detection mattered enormously, because strong gravitational lensing, this clean and this well-defined, had never before been confirmed in a galaxy cluster this far back in cosmic time, and it immediately raised the question of just how many similarly extreme, similarly ancient structures might still be sitting undetected in Webb's growing catalog of deep field images, simply waiting for someone to look at the right target with the right instrument. XLSSC 122 immediately set a new distance record as the most remote galaxy cluster ever confirmed to act as a strong gravitational lens, a title that matters for reasons well beyond simple record keeping. Gravitational lensing isn't just a visually striking phenomenon. It functions as an extraordinarily precise physical measuring tool, because the exact degree to which a foreground cluster's gravity bends and distorts the light passing near it depends directly on how much mass that cluster actually contains, including the vast majority of its mass that isn't visible at all. That invisible mass is dark matter, the mysterious substance that neither emits nor absorbs light, interacts with the universe almost exclusively through gravity, and is currently estimated to outweigh all of the ordinary. Visible matter in the universe, the stuff that makes up stars, planets, and everything you can actually see, by a ratio of roughly 5-1. Because dark matter cannot be observed directly with any telescope, gravitational lensing represents one of the only reliable techniques astronomers have for actually mapping out where it sits and how much of it any given structure contains, using the visible distortion of background light as an indirect but remarkably precise proxy for an otherwise completely invisible substance. When Finner's team ran the full strong lensing analysis on XLSSC 122's newly discovered arcs, using the precise geometry and distortion pattern of the lensed background light to reconstruct the cluster's underlying mass distribution. The result they got back was, if anything, even more surprising than the lensing detection itself. The dark matter at the very center of this cluster turned out to be packed together with an extraordinarily high degree of concentration, measured using a standard astrophysical model called a Navarro-Frank-White profile, which describes how dark matter halos are typically distributed from a diffuse outer edge down to a much denser core. The concentration value the team measured for XLSSC 122's core came out to roughly 6.3, a number that, compared against established relationships between cluster mass and concentration derived from clusters much closer to Earth and much later in cosmic time, sits well above what standard models would predict for a structure this young and this far back in the universe's history. In practical terms, this meant XLSSC 122 wasn't simply an early cluster that happened to look organized from the outside. Its very core, the densest, most gravitationally bound region at its center, had already packed itself together to a degree of tightness that standard cosmological models generally expect to take billions of additional years of gradual gravitational accretion to achieve. The research team's own published conclusion was direct about what this meant, stating plainly that this unusually high concentration contributes to a growing picture suggesting that massive structure formation in the early universe may be proceeding considerably faster than standard cosmological models currently predict. Sit with that conclusion for a moment, because it is a genuinely significant claim coming from a peer-reviewed paper, not a speculative aside, and it is worth remembering that this specific measurement, unlike many of Webb's other headline-grabbing early universe findings, did not rely on estimating a galaxy's brightness or stellar mass from its color and spectrum alone, but on a direct geometric measurement of gravity itself bending real light around a real physical concentration of matter. The prevailing model of cosmic structure formation, the same lambda cold dark matter model that underpins essentially all of modern cosmology, makes fairly specific, testable predictions about how quickly matter should clump together into increasingly massive, increasingly dense structures as the universe ages, starting from the nearly uniform distribution of matter left over from the Big Bang and gradually building up through the steady pull of gravity into the galaxies, clusters, and superclusters that fill the modern universe. Those predictions aren't arbitrary. They come from decades of careful, theoretical work, calibrated against enormous computer simulations and checked repeatedly against real observational data from the nearby well-studied universe. Finding a cluster like XLSSC 122, sitting at cosmic noon with an already mature stellar population, an already metal-enriched intracluster medium, and now, thanks to Webb, an already extraordinarily concentrated dark matter core, does not necessarily mean the entire standard model is wrong. Individual objects, even remarkable ones, don't overturn an entire cosmological framework on their own, but it does mean this particular corner of the model's predictions is under real mounting observational pressure. Joining a growing list of similarly surprising Webb discoveries throughout 2025 and 2026 involving galaxies and structures that appear too large, too massive, or too organized for how early in cosmic history they're being observed, because XLSSC 122 is not, in fact, an isolated anomaly. It fits directly into a much broader pattern that has been building steadily across the entire James Webb Space Telescope mission since its very first deep field images were released back in the summer of 2022. Throughout 2025 and into 2026, Webb has repeatedly turned up individual galaxies and structures that seem to violate the same basic expectation, that the early universe should look young, chaotic, and unorganized, and instead keeps looking startlingly mature. Earlier this year, astronomers using Webb's Cosmos Web Survey, an enormous imaging campaign covering more than 164,000 individual galaxies, produced the clearest map ever assembled of what's known as the cosmic web, the enormous filamentary network of galaxies, gas, and dark matter that connects structures across the entire observable universe, tracing that network back to when the universe itself was only about 1 billion years old and revealing dense, organized filaments and clusters already taking shape far earlier than researchers expected. Around the same period, a separate research team studying a massive galaxy formed less than 2 billion years after the Big Bang found it displayed essentially no rotation at all, a characteristic almost exclusively associated with much older, far more evolved galaxies rather than young, recently formed ones. And a team at Texas A&M identified an actively merging collision of at least 5 separate galaxies, occurring only 800 million years after the Big Bang, evidence that galaxies were already interacting, colliding, and reshaping their surroundings at a stage in cosmic history previously assumed to be too early for that kind of complex. large-scale interaction to be underway at all. Individually, each of these findings represents its own small, specific challenge to some particular corner of standard cosmological modeling. Taken together, alongside XLSSC 122's unusually concentrated dark matter core, they form a genuinely striking pattern, one that a growing number of astronomers now openly describe as a persistent and widening gap between what current theory predicts about the early universe and what Webb keeps actually finding when it looks. What makes XLSSC 122 stand apart from most of those other surprising early universe discoveries, though, is the specific nature of what Webb was able to measure. Most of the other examples involve individual galaxies, appearing unexpectedly bright, unexpectedly massive, or unexpectedly mature for their age. Important findings, but ones that are, in a sense, indirect, inferred from a galaxy's brightness, color, and spectral properties, rather than from a direct physical measurement of its total mass. XLSSC 122's gravitational lensing detection is different because strong lensing provides something close to a direct geometry-based measurement of exactly how much mass, including invisible dark matter, sits at the heart of this specific structure, independent of assumptions about stellar populations or star formation histories. That distinction matters enormously to working cosmologists, because it means XLSSC 122 doesn't just suggest something unusual happened here. It provides an unusually clean, physically grounded data point that can be directly compared against the same kind of lensing-based mass measurements astronomers have already collected from hundreds of much closer, much more thoroughly studied galaxy clusters throughout the more recent universe. Finner and his collaborators have been explicit about where this research goes next, and their own framing of it captures both the excitement and the genuine scientific stakes involved. As the team has explained it, this discovery is still, in a real sense, only the opening move. A single strongly lensing cluster, however extreme, however unusually concentrated, is still just one data point. And one data point, however striking, cannot, on its own force, a full-scale revision of established cosmological models. What can begin to do that is a genuine population of similar objects, enough strongly lensing clusters found at comparably early points in cosmic history to allow researchers to build real statistical confidence around whether XLSSC 122 represents a true outlier or an early hint of something more broadly true about how quickly structure actually assembles in the early universe. Finner himself has described strong lensing as an especially valuable, especially sensitive tool for probing dark matter, without ever needing to observe it directly, precisely because it offers such a clean, quantitative window into the cosmological models astronomers rely on. And with Webb's imaging power now demonstrably capable of pulling this kind of signal out of a cluster that Hubble, working on the exact same target years, earlier had entirely missed, the team has explicitly framed the next phase of this research as an active, ongoing hunt, searching Webb's growing archive of deep field observations for additional strongly lensing clusters at similarly early points in cosmic history in hopes of building the kind of statistical sample that could genuinely force a meaningful revision of existing cosmological models if the pattern holds. Following up directly on the initial lensing discovery, additional research led by Zachary Schofield and Hyungjin Ju at Yonsei University has continued digging deeper into XLSSC 122 throughout 2026, examining additional aspects of the cluster structure and stellar populations using the same rich Webb dataset, work that has further cemented the cluster's position as one of the most closely studied and most scientifically productive individual targets to emerge from the entire cosmic noon era of the early universe. The results of this expanding body of work were formally presented at the 248th meeting of the American Astronomical Society on June 17, 2026, and published as a peer-reviewed paper in the astrophysical journal Letters, cementing XLSSC 122's status more than a decade after it first appeared as a faint, easily overlooked smudge in an X-ray survey almost nobody outside a small community of specialists had ever heard of, as one of the most consequential single objects to come out of the entire James Webb Space Telescope mission so far. It's worth pausing to actually appreciate the scale of what's being described here, because the sheer distance involved makes it easy to lose track of just how extraordinary this object actually is. Light left XLSSC 122 roughly 10.4 billion years ago, meaning the photons Webb captured in its recent images began their journey across the universe before our own solar system had even finished forming, before the sun itself had ignited, crossing an almost incomprehensible stretch of expanding space and time before, finally reaching a mirror built by humans on the other side of that journey. And what that ancient light revealed wasn't a young, chaotic, half-formed smear of newly forming galaxies, which is exactly what standard cosmological models predicted astronomers should find at this specific point in cosmic history. It revealed something that, structurally, dark matter core and all, already resembled the kind of massive, organized, gravitationally mature galaxy cluster you'd expect to find much closer to home, in the well-studied, comparatively nearby universe billions of years further along in its development, a city already built where the blueprint said there should only be scattered foundations. It's worth understanding exactly why Hubble, despite spending years studying this exact same cluster in remarkable detail, never caught the lensing signature that Webb picked up almost immediately. Hubble's Wide Field Camera 3 is an extraordinarily capable instrument, and it was Hubble's spectroscopy, not Webb's, that originally nailed down XLSSC 122's precise redshift and confirmed its unusually mature stellar populations back in 2020. But strong gravitational lensing arcs from an object this distant are faint, subtle, and require both exceptional resolution. An exceptional infrared sensitivity to distinguish clearly from the surrounding cluster light and background noise. Webb's much larger mirror, combined with detectors specifically optimized for the redder, more infrared, shifted light that objects this far away and this ancient inevitably produce, gave Finner's team a fundamentally sharper, cleaner view of the same patch of sky Hubble had already studied for years. It's a pattern that has repeated across several of Webb's most significant discoveries since 2022. Cases where the raw data needed to make a breakthrough had, in some sense, already been sitting within reach of earlier. Telescopes, just below the threshold of what those instruments could actually resolve clearly enough to recognize. Right now, in the summer of 2026, XLSSC 122 remains, by a meaningful margin, the most distant galaxy cluster ever confirmed to display strong gravitational lensing. A record that stood unbroken from the moment Finner's team's paper was published, and that will remain in place until another team, somewhere, finds an even more distant example doing the exact same thing. Given how explicitly Finner and his collaborators have framed their ongoing search for additional clusters like it, and given how many other unexpectedly massive, unexpectedly mature early universe structures Webb has already turned up across its first several years of full operation, that record may not stand indefinitely. If more clusters like XLSSC 122 do start turning up, and turn up in meaningful numbers rather than as isolated curiosities, the implications reach well beyond a single distant object or a single broken distance record. It would mean the fundamental timeline by which the universe assembles its largest, most massive structures needs a genuine substantive rethink, not a minor footnote adjustment, but a real reconsideration of exactly how fast gravity was able to organize matter, including the vast, invisible reservoirs of dark matter that make up most of the universe's total mass during the earliest, most poorly understood chapters of cosmic history. If you want to be here when the next strongly lensing early universe cluster gets confirmed, and you want it explained with the real data intact, rather than flattened into something simpler and less interesting than what actually happened, subscribe now and turn on notifications, because Finner's own team has said plainly that this is only the beginning of the search, and the next entry in this growing, deeply strange catalog of structures that shouldn't exist yet may already be sitting somewhere in Webb's archive, waiting for the right team to look closely enough to find it. 10.4 billion years ago, a cluster of galaxies finished organizing itself into something far more mature than the universe around it had any right to produce, and it has been waiting patiently in the dark for the better part of 11 billion years for an instrument sharp enough to finally notice.